Water exchange rate is based on the culture tank size, the fish biomass, and the daily feed rate. Okay, we know that, we've already talked about that. It's based on how fast ammonia is getting produced in that tank and how fast we actually need to move the water through there to get it out and process through the biofiltration. Undersizing of the mechanical filtration portion will result in inefficient solids removal and mechanical failures. So if you undersize it, you're not going to remove all the solids that you want, and that might overtax your next size of filtration, or you're going to have mechanical failures because you're pushing it too hard, it's working too hard. In that case, like a drum filter, if you size it with way too small of a screen and too small for the application, it might just turn completely 24/7, never have a break in between, and that can cause the motor to burn out quicker and seals to fail quicker. So oversizing will result in more upfront costs for the equipment, a larger footprint for that equipment, as well as a larger amount of wastewater removed from the system per day if drum screens are sized too small. So on average, a drum screen filter removes 10% of the water per day by washing that screen. Well, just by that math, you can see in 10 days, that would seem like 100% of the water would be turned over. In actuality, when you factor that out, it would take 16 days. But every 16 days, you would actually be turning 100% of that water out of the system. Well, in aquaponics, especially a recirculating system, that would be really bad. That means every 16 days, 100% of that water is getting flushed out of the system. And that's bad because you're just flushing those nutrients that we want to save and let the plants take up. The biofilter converts ammonia to nitrate nitrogen through the process of nitrification. We've done this, we've gone through this. Very important to remove the solids before the biofilter so we don't foul the biofilter. We want to maximize autotrophs, minimize heterotrophs. So maximize our autotrophic bacteria, which are nitrifying bacteria that are going to process that ammonia, and minimize the heterotrophic bacteria, which are more eating your organic matter. They're not going to be processing ammonia to nitrate nitrogen. We want to create a hospitable living space for nitrifying bacteria. So clean, high oxygen, high surface area filter, which we've talked about in the sizing portion. They come in many sizes: moving bed bioreactors, trickling filters, bead filters, fluidized bed sand filters. All surfaces of your tank, piping, the deep water culture walls, the bottom of the rafts, the plant roots, etc. All of that accounts for surface area, and anywhere there's a surface, the bacteria is going to have a place to fix, stick to, and actually proliferate. Passive nitrification can account for up to 30% of the total nitrification in a recirculating system. So not even taking into account plant beds, just in a recirculating aquaculture system, passive nitrification on the surfaces of the tank walls, on the surfaces of the pipes, on everything that's covered in water, just that can account for up to 30% of the nitrification needed in that entire system. So that's kind of shocking, and that's good to know, because if we size our biofilters correctly, then there's a little bit of a redundancy built in there by the passive nitrification naturally occurring on the surfaces in the system. The main factors to look at when we're designing a biofilter or purchasing a biofilter are the available surface area on the media, the volume of the media, the friction losses going through the filter, the footprint that it's going to take up, the total price, the energy to operate, and the ease of use. Biofilter designs are based on the media's specific surface area expressed in square feet per cubic feet or square meter per cubic meter. So we're basically saying for every cubic foot or meter, so a basic volume of this plastic media, we're going to get so many square feet of surface area, so flat surface area within a given volume. That's what we're telling here by this number. Aerial TAN conversion rates here, or it's called an ANR, are expressed in grams of total ammonia nitrogen converted to nitrite per day. And of course that would mean also the same of nitrite converted to nitrate per day. for the rest of the nitrification process there. But these conversion rates, since we calculate our TAN amount already to do our water flows, and we've already talked about that, it's really easy. We know how much TAN we are producing per day, and we can use that to tell how much of the surface area in a filter we need to convert that TAN to nitrate nitrogen. Volumetric TAN conversion rates in grams of TAN converted to nitrite per volume per day. The media purchased by the cubic foot or by the cubic meter, and the biomedia is actually given a specific surface area and TAN removal rate. So here's an example for a moving bed bioreactor, MBBR. If K1 media, that's a coldness media, a plastic biocarrier media that we use in a moving bed bioreactor type of biofilter, well, that specific type of media has a number of 259 square feet of surface area for every cubic feet of volume of media that you put into your filter. So again, 259 square feet per cubic foot. And this is a K1 coldness media moving bed bioreactor quick sizing reference chart. So for every 1.2 pounds of food that we feed into the system, it requires 1 cubic foot of media, of biomedia, to process that per day. So 1.2 pounds of food per day per cubic foot of media. And for a K1 MBBR, the tank volume should be 2 times the volume of the K1 media. So if we calculate that we need, say, 4 cubic feet of K1 coldness media to process the total ammonia nitrogen, then we need 8 cubic feet of total tank volume, because we only want to fill it halfway with the media. 70% is really the max fill rate that we can still actually get it to move in there, but shoot for 50, and that way if you ever needed to add more, you have a little bit of a buffer zone to add more into the biofilter. The tank size should be a 1-to-1 height to diameter ratio for the best mixing. So for the lowest requirements and power requirements and best mixing within the vessel, a 1-to-1 ratio. So 3 feet high, 3 feet diameter. The tank volume times 0.25 equals the flow rate in gallons per minute. So it's a real quick way. These have a range that you can flow through, but this is a safe number that you can quickly size the flow rate through that biofilter to actually allow it to process the ammonia. So again, 100-gallon tank times 0.25, so 25% of that gives you 25 gallons per minute flow through that tank. For an added safety factor, you can just aim for a 5-minute retention time on that, which would, again, this is a 4-minute retention time, 25 gallons per minute in a 100-gallon tank. So if we brought that down to 20 gallons per minute, that really gives us a safe number, 5-minute retention time, plenty of contact time in that vessel for the biofilm on those carrier elements to oxidize the ammonia. The aeration requirements for a K1 MBBR are 5 times the tank volume in cubic meters per hour. So 1 cubic meter per hour equals 0.589 CFM, that's cubic feet per minute, and that's what a lot of the aeration devices in the US are going to be sized under. I believe in Europe it could be, again, cubic meter per hour or liter per minute. You may see that as well and do that conversion factor. But this is very simple. We're multiplying our volume by 5. So we have 0.25 cubic meters in an MBBR tank, and we're going to multiply that by 5. 5 times that gives us 1.25 cubic meters per hour, or after we convert that to CFM, it's 0.74 CFM of air. So 264 gallons per cubic meter. That's just a conversion factor if you need that. 264 gallons of water equals 1 cubic meter of water. So 1/4 of a cubic meter of water equals 66 gallons for the tank. And that right there just gives you some good numbers to use. You can click this link and there's a lot of conversion units there that can help out, because you've seen throughout this entire course, especially the last session and this session, there are a lot of conversions that we go through, and especially when we're trying to teach to America and then the rest of the world that uses metrics. So use the conversion units and you will get the correct answers. Let's do another quick example here. Size and MBBR for 1,000 pounds of fish eating 2% of their body weight per day. Okay, it's 72 degrees Fahrenheit. Well, we know 2% of 1,000 is going to be 20 pounds, 9 kilograms of food per day. A K1 colonist biomedia will process 1.2 pounds of food per cubic feet of that media. So, really easy, we divide this by 1.2 and we get 16.6 cubic feet of colonist media needed in that biofilter. Well, how big of a tank do we need? We want to multiply that by 2. So the volume is 33.3 cubic feet for the tank that's going to hold this media. 7.48 gallons per cubic foot. So we just multiply that together, 33.3 times 7.48, and we get a 249 gallon tank to hold this media. 0.94 cubic meters times 5 gives us 4.7 cubic meters of air, or 2.77 cubic feet per minute of air within this vessel. That took us how long? A minute, 2 minutes? We sized an entire biofilter for 1,000 pounds of fish. Once you get comfortable, these are not very hard to do. And again, we're using quick references here for colonist media. For other medias, we have to actually look at how much ammonia they can actually process per day, what our flow rate's going to be through that unit, and so on and so forth. But this is, what I'm covering within our course. And if you want to know more about biological filtration, by all means, I can point you in the right direction and answer any other questions that you may have on that. So here again, calculate daily feed amount, calculate volume of media needed, calculate biofilter tank size, calculate aeration, calculate flow rate, purchase or build an appropriate sized biofilter for the space and the project at hand. In a decoupled aquaponics system, you must include a biofilter in the design. There's no question. It's just like a recirculating aquaculture system because the fish system is independent from the plant system. So there's no using the plant bed as your biofilter. You must include one in. This is a very crucial part of the life support package. In a recirculating aquaponics system, it's still smart to include a biofilter in the design, just in case of an emergency where those components need to actually be separated. So for instance, let's say you have your fish that actually come down with some kind of disease, something happens, and you need to actually treat the fish system, maybe with salt, maybe with an antibiotic in a worst case scenario. Well, you don't want that flowing into your plant system, and you don't want to completely shut your operation down. So you can valve off the fish system, decouple those two components, treat the fish system while it still runs as a recirculating aquaculture system, and then allow your plant system to continue to grow. Now, generally in a deep water culture system, you have 2 to 4 weeks of nutrients that are going to be in there before you start to see deficiencies. So you have a bank of nutrients that can help you get through a hazardous situation. But in a worst case scenario, you could also convert your system to hydroponic nutrients and keep the product and cash flowing until your fish get back on track, then recouple the two components. So you're mitigating risk by including a biofilter within your filtration package on a recirculating aquaponics system. The University of Virgin Islands has no biofilter, as the surface area in the raft beds and on plant roots is more than sufficient for nitrification, which was less expensive to start, but it's more of a risk, which we just talked about. I think that was one of the key points to developing the University of Virgin Islands system, was to make aquaculture cheaper. And one of the, something that's a little bit pricey when building an aquaculture system is building the biofilter. So by getting plants to act as a biofilter and by allowing the trough to act as a biofilter, they were able to eliminate that piece of filtration package and have it work good for, again, 30 years. So it works, but my recommendation would be to include a biofilter in your filtration package. So the plant component should be sized and designed based on the type of plant being grown, the nutrient availability from the recirculating aquaculture system component, and the climate that you're in, okay? So nutrient availability is directly related to the feed input, and it's going to be represented by the following equation, and that is PA equals F divided by PF, where PA is our plant area in either square feet or square meters, so the growing area that we're going to have of plants. Our F is our daily feed rate, so how much we're feeding into the system per day in grams. And then PF is going to be our plant uptake factor in grams per square feet or grams per square meter, depending on if you're doing this in square feet or square meter, okay? So actually very simple. We're going to take our feed input, divide it by what the plant needs, how many grams per square foot the plant needs, and that gives us the plant area that we can grow. Now, I will state that this is done at 76 degrees temperature, okay? That's where these were calculated at. And if you go below 76 degrees, you're going to slightly need a higher nutrient level in the water. Okay, as the colder it gets, it's harder for plants to actually pull nutrients out of that water column. And I really wouldn't do much of a change to the chart until you got down to, say, 60 degrees. If you got down to 60 degrees, I would increase these values by 10%. That's the only caveat that I would lay to this. So here is a chart of your plant uptake factors. And this is a wide variety of vegetables. If you have something else you're growing, you can always message me and I'll give you a plant uptake factor for that, because I have several others that I didn't include in this presentation. I didn't want to make 20 pages of just factors here within the presentation. But anything you don't see here that interests you, by all means message me and I'll try to get you that number. But you can see we've got artichokes, asparagus, common beans, broad beans, beetroot, broccoli, Brussels sprouts, cabbage, capsicum, which is your bell peppers, carrots, cauliflower, celery, cucumbers, eggplants, endive, garlic, leek, lettuce, okra, onion, pak choi, parsnip, peas, potatoes. On this chart, you have your variety, you have your plant factor values, and you have the desired pH that that plant would like to grow in, and that is for maximizing the nutrient uptake of that plant. So we can have everything else right, but if you're not within the given pH range, it's going to be hard for the plant to naturally absorb those nutrients. And here we have some more varieties: pumpkin, radish, spinach, Swiss chard, which is called silver beet, squash, strawberry, sweet corn, sweet potato, taro, tomato cherry, tomato slicer, turnip, zucchini, and 90% of the herbs here that fall within a PF value of 1.2 for as far as your plant nutritional needs, and they fall within a 5.5 to 6.5 on the pH scale. Deep water culture is preferred for most crops due to your lower overall risk, high growth rates, adaptability to plant requirements, and the ease of use. So when I talk a lot about risk. Well, deep water culture is much lower risk than, say, a vertical apparatus, than a gravel bed, than an NFT system, even than a Dutch bucket, because you have a large bank of nutrients and of water. Because you have that, you have a more stabilized environment, and in case something happens, power outage, pump failure, aeration out, something like that, you're going to have the plants actually survive, and it's not going to severely cripple your business without giving you time to fix that problem. So it's much lower risk than a lot of the other technologies that we'll talk about on a later on session. Any type of component used to grow hydroponic plants can be used in aquaponic production. This is the combination of aquaculture and hydroponics. So we can use any of those hydroponic components as long as we treat our water coming from the recirculating aquaculture component properly. And that means the proper filtration and the proper pre-treatment to give the desired product going into that hydroponic apparatus. So the University of Virgin Islands deepwater culture trough design is right here. They use 0.3 CFM or 8.5 liters per minute of aeration delivered through 3-inch air stones that are placed every 4 feet or 1.2 meters down the length of the trough. So a 3-inch stone every 4 feet down the length of the trough. Their troughs are 16 inches deep with 4 inches of freeboard and 12 inches of water. So 16 inches deep, but they only fill the water up to 12 inches, allowing 4 inches of freeboard in case of a rainstorm or some kind of water change, or they need to move water in there to say, harvest a fish tank. It allows them extra water storage capacity. The flow passes through 2 troughs, which is 200 feet in length, before draining back into the sump. And they're constructed of cement block and lined with a food grade liner. So the Chatterson Farms deepwater culture trough design is I use 4x4 posts placed every 4 feet down the length of the trough, and I put 3 feet of it into the ground with 1 foot of the 4x4 exposed. We take a 2x12 wood plank and we use that as the trough sidewall and screw that into the 4x4 posts. Then we take a 2x6 board and we use that as a cap, as a railing or bench, and that's placed on top of the 4x4 posts, which is already attached to the 2x12 sidewalls. This is very simple, very robust, and an inexpensive design. I can tell you personally, having built these, that once I have a post hole digger that I went ahead and bought since I didn't want to hand dig a couple hundred post holes for this project. So I bought that. I want to say it was $250 for the post hole digger, gas powered. And in one day, I can construct a 100-foot trough by myself. One day, from zero to doing the holes, placing the wood in, attaching everything, lining it, and putting the plumbing in one day. And if I can do that by myself, I know that with a team of people, you could knock out something fairly easily, you know, even on a large scale. I'll show you a picture of the troughs in just a second. On my troughs, the trough is again lined with a food grade liner, which is wrapped over the side walls, and then it's stapled to the outside of the trough. Then the excess liner is trimmed. I also use 0.3 cubic feet per minute of aeration delivered through 3-inch stones every 4 feet down the trough. I use a manifold constructed with a valve at every 4-foot stone so that I can equalize the air pressure throughout those stones. As we've mentioned, air will move the path of least resistance, so as some stones maybe get clogged or as it's further on down the run, you're going to get less air out of those stones because of friction losses. But if you add a valve, you can equalize those at the start of the operation and then have a clean run throughout the entire run. University of Virgin Islands does not use valves. They actually just put a barb into their main pipe and feed off of that. So it's actually not regulated at each stone. There's a big difference there. The bulkheads, to drain and plumb in and out of these troughs, I use bulkheads just like in the fish tanks, and I plumb under the floor. So not through the sidewall, but directly through the floor at the beginning and end of the troughs, and then come under the sidewall and plumb to where we're heading with the pipe. Water flow in a coupled system using aeration. So we have a fish tank, a plant portion, and the water's running through the entire thing. Should be 1 turnover every 1 to 10 hours. So we want the fish tanks to turn over at the correct rate that we calculated earlier off of ammonia production. But the plants don't really care. We have enough of a bank of nutrients that you could only turn that plant portion over 1 every 10 hours and the plants would still be fine. So this is really more for the plants, but I would, in this type of system, use size off of the flow in the culture tanks to provide the right habitat for the fish and just allow the plants to take that flow. And it will fall within that 1 to 10 hour range. Water flow in a coupled system using pure oxygen, okay? So if we're using pure oxygen in the fish tanks and pure oxygen in those plant troughs, should be 1 turnover every 1 to 4 hours. So we need higher circulation because we're not using air stones. And by nature, as air moves up, it mixes. So you're going to get a lot of mixing within those troughs. But using pure oxygen, you need a higher turnover out of the pump to make up for the mixing you're not getting from the plume of air bubbles. Water flow in a decoupled system using aeration is not needed. So if it's decoupled and we have a plant portion and we have a fish portion and we're just using air, the air movement alone is enough to mix that water that we don't actually need a water pump to move the water also. We get enough mixing action with the air. Water flow in a decoupled system using oxygen, again, I would revert to the 1 turnover every 1 to 4 hours in the plant portion. On the fish portion, we would size, again, off of our ammonia production. So oxygen requirements for deep water culture beds. Don't hear this talked about much, but if you're using pure oxygen, you have to know how to actually size that device, how much oxygen these plants are taking in. Not just the plants, but the biological oxygen demand of the bacteria, the other life living in those plant troughs. So here's the calculation for you. 0.108 grams of oxygen per hour per square foot of growing area of plants. This comes out to be 0.000237 pounds of oxygen per square foot, or 0.095 pounds of oxygen per 100 by 4 foot trough. So if you just want to look at things in a 100 foot by 4 foot trough basis to get that idea of oxygen consumption, there's your number. We want to size the oxygen requirements, then choose a sufficient oxygen supply, whether that's a generator or a tank using liquid oxygen. And then we want to size the saturation device, the water pump, and then create the plumbing scheme to ensure equal mixing within that vessel. After that, we've basically designed the entire thing and we go ahead and we install it in the system. The rafts themselves, the floating polystyrene rafts, are commonly made out of 1.5 inch or 2 inch Dow blue board. And this is extruded polystyrene, which is purchased from Lowe's or online. And I've used frpshop.com in the past. There's several other places that sell this because it's a common insulation used in building projects. Make sure to purchase the square edge and not the scoreboard. Scoreboard has tiny scores in it that's made to break and fit into walls of houses. You don't want your rafts to break easily when you're investing this kind of money on them. So get the square edge variety. You can purchase thinner food grade pre-made boards from Beaver Plastics in bulk. So Google Beaver Plastics and you will see the food grade boards. The thing that I don't like about the Beaver Plastics is in a heavy aerated system, you get the plume of water that comes up. Well, with a 1/2 inch board, that plume of water can rise right up through the holes and cause crown rot right at the base of that lettuce plant or whatever plant you're growing. So they're not my favorite in a heavily aerated system. But in an oxygenated system, I think they'd work just perfect. And plenty of people use these worldwide, so we know they work. The other good thing is that they're actually certified food grade instead of just being a polystyrene. That some people have concerns that there's fire retardants in some people have concerns that they're made by Dow. So you're going to have to make your own decision on what you purchase here. I use a Dow blue board in our systems here at Chatterson Farms. Now, we were actually able to specify that we wanted no fire retardants when we bought these boards several years ago, and I don't think that's as easily to do now. So now I would be looking at purchasing locally, and you purchase a virgin polystyrene from local builder supply store. Most large cities have people that are extruding polystyrene for commercial businesses, for building projects. So do some research and see what you can find locally, and they will go ahead and run a load just for you without fire retardants, which is great. We don't want any of that in our food supply. 8 inch centers are popular That's what I use on all of our rafts. We drill them at 8-inch centers because we grow a wide variety of vegetables. And if I have something that needs a wider planting scheme, then I skip a hole and we just plant at the needed variety. We still don't have any issues with algae, anything like that, but that's what I do. Now, let's say you set up a whole operation just to grow Bibb lettuce. You would probably drill everything at 6-inch centers. Or if you were just doing tomatoes, you would just drill the appropriate spaces for those tomato plants, maybe every 24 inches, and we would leave the center solid. We wouldn't drill any holes out there because you're not planting into it. So we can take a look at what you're growing, and that will tell you how dense and what kind of spacing to actually drill out of these boards. And here you go. Here's a beautiful picture of the University of Virgin Islands. They've got their fish system back here covered. Here's the 6 100-foot troughs. And you can see it's nice and straight. These are all made out of cinder block. Food grade liner goes over the side, and then they have a board actually nailed to the side to hold that liner tight against the side of the frame. Here's a picture of the troughs built here at Chatterson Farms. And you can see this is before we put any ground covering in. Actually, I had some, but it got really covered in sand because we built on basically a beach. But before we got covered up with our new ground cover, you can really see how these were constructed. 4x4, 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 every 4 feet going down. Then we go on the inside and we just stick a 2x12 plank against it. I bought 16-foot 2x12 planks. So basically one plank covered 4 of these sections. That would be one board. Stick it up there, drill it in to each plank, move on to the next one. So it was very easy to build the sidewalls, and then after we were done, I just put a 2x6 on the top, right down, screwed down into the 4x4s, and then into the top of the 2x12, and then we wrapped that with the liner. So 3 different pieces of wood, 4x4, 2x12, 2x6 cap, and then we wrap that with the liner. Now, I love this railing because I can actually stand on that railing if I'm going 8 feet up trying to mess with tomatoes or cucumbers or something else up on a ledge. I can sit on that ledge if I'm going to be harvesting and my back hurts and everything's down at a lower level. You can sit down and harvest and move everything right onto a cart. It's very easy. So this comes in handy. I see a lot of troughs made with the real thin railing, and I don't like that. I would rather take up the extra 2 inches of room in the greenhouse that takes and use that to sit on. So also I used 4x4s, so we already had the width there. We didn't have to go out any further. So since the floor footprint was already used, it didn't make any difference there to add a top rail. I really like these, and I would construct them the same way in the future. Caution, less air is going to result in staggered growth around the diffusers. So if you don't deliver the required air that we talked about, or you let your diffusers clog up and there's not the sufficient amount of air coming through them, you're going to see staggered growth. You'll see nice growth right above the diffuser and slower growth to the outsides. It will actually look like a wave of growth because of the placement of these diffusers every 4 feet. Longer troughs are possible with multiple water injection points down the length of the trough. So instead of having all the water go into one point, we would split that up into multiple injection points. Say if you wanted a 400-foot, 1,000-foot long trough for whatever reason, as long as you split the water flow up down the length, it would be equally mixed and the plants would still get the nutrition that they need. If you're monocropping, meaning growing one specific crop at a time, just basil and that's it, or just lettuce, I suggest don't go over 150 feet without multiple injection points due to possible nutritional deficiencies occurring at the end of that run. So I've seen in the past in some of my customers and even in the University of Virgin Islands where they could see nutritional deficiencies at the end of that run because the water had actually had the nutrients pulled out in great enough quantity by the time they reached those vegetables that the vegetables showed deficiency symptoms. This is a beautiful picture of Bright Farms. So Bright Farms is a hydroponic operation, but you can see here any size trough is possible. So when we're using controlled environmental technology, an expensive greenhouse, that you're paying $100,000 for, you have to pay for the lighting, the heating, the cooling, the water temperature cooling, all the aspects to create the perfect environment. You want to be able to fit as many plants in that space as possible, because that's how you make money. You're not going to do it with a big aisle down every space and in between, because it costs you too much per square foot to keep the environment in that greenhouse. So as you can see here, there's almost no walking room in this entire facility, but it was engineered that way. They have their means to harvest these. They'll harvest from one end, or they actually have a thin walking plank at several areas in here. And they can harvest these entire crops, plant from one end, push them down and harvest from one end, and make use of that entire square footage of the footprint of the greenhouse. And if you want to maximize profits, especially on a large scale, that's the kind of design you need to be thinking about. And that's it for this session. Again, if you have any questions at all, please email me, ryan@collegeofaquaponics.com, and I will be sure to cover those questions in our weekly question and answer session and make sure you get all the information that you need. Thank you very much.